We always think that complex problems need, well, complex solutions, right? But what if I told you the secret to building some of the most massive, powerful software out there is actually a simple four-step plan? Let's dive in and break it down.
I mean, just think about the apps you use every single day. Their performance seems so effortless, right? But behind the scenes, it's often a total storm of complexity. The amazing thing is, there's a surprisingly simple roadmap for taming all that chaos. And that's exactly what we're going to get into today.
Okay, so first things first, let's actually understand the problem we're trying to solve here. It's a really fundamental challenge in modern computing, and it's called the concurrency puzzle. Have you ever stopped to wonder how a service like Netflix can stream movies to millions and millions of people all at the same time? Or how a huge online game with thousands of players doesn't just, collapse? Well, the magic behind all of that is this one concept, concurrency. It's basically the art of doing a whole bunch of things at once.
See, back in the early days of computers, everything was pretty simple. Programs would just run sequentially, one step right after another. It was predictable, sure, but man, was it slow. Fast forward to today, and our systems have to juggle just countless tasks all at the same time. And while this is incredibly powerful, it also, it opens the door to some serious chaos if you don't manage it just right.
Yeah, and this quote from our source material, it just hits the nail on the head. Concurrency is a powerful tool for sure, but trying to get all those pieces to fit together perfectly without anything breaking, it can be absolutely dizzying for the people building this stuff. And believe me, the risks are very, very real. You could have different tasks using old, outdated information. Or what if two tasks try to update the exact same piece of data at the same time? Boom, you get corruption. You can even get these things called deadlocks, which is exactly what it sounds like. The entire system just freezes up, waiting for something that's never going to happen. These are the dragons we really need to slay. So, the big question is, how do we solve this dizzying puzzle? Well, it turns out there's a simple, really elegant plan for it. It's called Foster's design methodology. And the absolute genius of this approach is that it forces you to think about the problem first, way before you even think about writing a single line of code. All right, here they are. The 4 simple steps to tame all that concurrency chaos: partitioning, communication, agglomeration, and mapping. Now, let's break down what each one of these actually means, and we'll use a pretty simple analogy to make it stick. Let's imagine you're planning a big road trip with your friends. What's the very first thing you do? You'd take that massive, overwhelming task of plan the trip, and you'd break it down into smaller, manageable jobs, right? That's partitioning. You're not actually doing anything yet. You're just identifying all the little individual pieces of work that need to get done. And it's the exact same idea in software. The goal is to take a huge problem and just decompose it into the smallest possible tasks you can think of. You're basically looking for all the little pieces that could, in a perfect world, be worked on at the exact same time. This first step is all about finding the absolute maximum potential for doing things concurrently. Okay, so back to our road trip. You've got your list of jobs. Now what? Well, you need to figure out how everyone's going to coordinate. Who needs to talk to whom to get things done? You'd probably just start a group chat, right? And that, right there, is the communication step. And in our software, this is the point where we figure out which of those tiny little tasks actually depend on each other. If one task needs some piece of information from another one, how are they going to share it? You're essentially drawing out the entire map of communication before a single bit of data actually starts flowing around. All right, now we're on to step 3, agglomeration. And this one is all about being efficient. Think about the road trip again. It just makes sense to group similar tasks together, doesn't it? Like if one person is already booking the hotels, they're in the perfect spot to also look up good restaurants nearby. Now, this is a really crucial step. And I know, it might seem a little counterintuitive. I mean, didn't we just break everything down into the tiniest possible pieces? Yes. But now we strategically group some of them back together. And why would we do that? Because it seriously reduces the amount of communication, the chatter, you could call it, between tasks, and that saves network bandwidth, it cuts down on processing overhead, and it just makes the whole system run way more efficiently. And finally, we have step 4, mapping. So we've defined the tasks, we've planned out the communication, and we've created these smart, logical groups. Now it's time to actually assign the roles. This is where you decide who, or in the world of computers, what, is actually going to do the work. So, in the world of software, this means we're assigning our carefully crafted tasks to actual physical processors or different computers in a network. The whole goal here is to keep every single processor as busy as possible, doing useful work, and not just sitting around twiddling its thumbs waiting for data from another one. Okay, so that's the theory. Sounds pretty good, right? But how does it actually work in practice? Let's see this plan in action by applying it to a really classic computing problem, counting a whole bunch of words. So check out this fascinating bit of history. Way back in 1631, a printer in London made a tiny but pretty major typo. They left the word not out of one of the 10 commandments. Yeah, the result was what we now call the Wicked Bible, and it highlights a really serious problem. How do you accurately process just massive, massive amounts of text without making a critical mistake? So let's imagine our job is to prevent something like that from ever happening again. Our task? Count every single word across millions of documents to make sure everything is 100% accurate. How could Foster's four-step plan help us tackle such an enormous job and do it concurrently? Well, here's exactly how it would map out. First, partitioning. The task is simple. We break down that giant library of documents into individual words. Easy enough. Next, communication. We decide that all of our worker processes will just access the files from one shared location, like a shared drive. Then, agglomeration. To cut down on all that chatter, each worker is going to do a pre-summary, a preliminary count of its own words before it reports back to the main system. And finally, mapping. We'll have a central scheduler, kind of like an orchestra conductor, that assigns files out to all the different workers to process. See? It's simple, it's logical, and it's totally scalable. You know, all of this really brings us to the single most important lesson from this whole methodology. It's not just about a neat little four-step process. It's about a golden rule that applies to pretty much all good design. And this quote from the source material, it just says it all perfectly. The temptation is always to jump straight to the tools, right? To think about the specific hardware or the programming language you're going to use. But that's the biggest mistake you can make, choosing those mechanisms before you've even designed the solution itself. And that really is the golden rule. Foster's methodology forces you to think about the what long before you worry about the how. First, what are the fundamental tasks here? Second, how do they all need to communicate with each other? By solving this more abstract puzzle first, you end up creating a really robust design that isn't locked into any one specific technology. It's just a good plan. So, we've seen how this simple plan contains some incredible complexity in software. But this way of thinking, it applies so far beyond just code. I mean, think about managing a team project or even organizing a city. Where else could this kind of methodical design be the absolute key to turning chaos into clarity? That's definitely something to think about. Thanks for joining me for this explainer.